All right, guys, this is a lecture on section 17.1. Um, so this is our last and final chapter. This chapter focuses on vector fields. There's a lot we can do with these things. This is um, this particular topic you're going to see throughout your physics classes when you get to electromagnetism. But it's super interesting. Anyways, I wanted to start you off with um, going through this section with you because there's some tricky stuff towards the end that might be helpful for me to explain. It may or may not be better than what you see in the publisher videos. So I'll just go through the whole thing. You don't need to watch this, but it's up to you. Okay, so a vector field. Hopefully you guys can see my screen. So a vector field is simply a collection of vectors. So I've given you a bunch here. This is a two-dimensional vector field because it's occurring in the plane. This is a visual representation of the vector field of wind in the United States at a particular point in time. And you can see that the vectors point in different directions, indicating the direction of the wind, and then the length of the vectors indicate the speed of the wind. Okay, here's another example. So if you've studied a little bit of electric forces in physics, you might have seen something like this. The electric force field of 2-point charges, one positive over here and one negative over here, creates a vector field, and we can represent this vector field visually using something like this. You can see that the vectors are leaving the positive charge and going into the negative charge, and the vectors are longer over here, indicating a stronger electric field, and longer here, indicating a stronger electric force there, and smaller over there in the middle. Here's an example of a three-dimensional vector field. So the gravitational forces due to Earth's gravitational field are shown in the visual below. So you can see Earth down there in the middle. Make this a little bigger. And you can see that you have these gravitational force vectors that are pointing inward, and the further you get away from Earth, the smaller the force, and the closer you get to Earth, the larger the force. There's plenty of examples of vector fields, including, circulation of water in a heat exchanger would be something like this one. Magnetic and electrical forces. I've already done electrical forces. This would be magnetic forces. Over here is a U-shaped magnet. Hurricane wind forces, you could do that in 2D or 3D. Here's a kind of a 3D semi-representation of a vector field. The stress and strain of forces on buildings and bridges, the transport of chemical pollutant in a lake, and human migration patterns. So there's lots of examples. You can take the idea of vector fields and extend it up beyond 3 dimensions. But for our purposes, we're just going to stick with vector fields in 2 and 3 dimensions. Okay. All right. So let's start with what a vector field is in 2 dimensions. So I've shown you kind of what it looks like, or a visual representation of them. But mathematically speaking, a vector field is it's a vector valued function on R2. Vector value means the output is a vector, and it's on R2, so the input is in R2. So here it is, a vector field on a region R of R2. There's your vector valued function. You'll notice it takes in an X and a Y value in R2. So you give it an X and a Y value, you plug it into the first component and the second component, and it's going to pop out 2 components, and you have triangular braces around them, meaning the output is going to be a vector. That's why that's in boldface. Okay, so that's mathematically speaking what a vector field is. Now to visualize these things, what we do is we plot a representative sample of these vectors using some grid points. We call them field points, basically to illustrate the general appearance of the vector field. So, for example, here's a 2-dimensional vector field. You can tell it's 2-dimensional because it's got 2 components there, just like this has 2 components. So this first component would be the f function, and the second component would be the g function. And you can see the output is a vector. All right, so how do you visually represent this vector field right here? Well, you can do it by first plotting a bunch of grid points and then calculating the vectors at each one of these grid points, like so. Now you might ask, how do you do this? Well, it's actually really easy. It takes a long time to do, but it's relatively easy. So let's say we wanted to figure out this vector right here at that grid point, this one right there. You'd look at the coordinates of the point, that would be x equals 2 and y equals 2, and you just plug x equals 2 and y equals 2 into the vector field, and you'll get out the vector, let's see, -4, 2. So your vector should be pointing to the left, should go over to the left 4 units and up 2 units. So it's going to look something like this. Now, I didn't actually go over 4 units and go up 2 units. And the reason why is because if I did that and we had all these grid, if we did it at all these grid points, everything would be overlapping. So what we do is we shorten the vectors down to a manageable size, and we keep their sizes in proportion to each other. So that way we can kind of see a general picture of what's going on. Okay, so you're going to do that for every single one of these field points. You know, doing this would take a long time to do by hand. So fortunately, we have programs to help us graph these. So that Math3D program will do 3-dimensional vector fields, and the Wolfram Cloud will do 2- and 3-dimensional vector fields. You can probably also find something online if you're interested in that. So that's what this vector field would look like visually. That's the general appearance of what the vector field looks like. Okay. Now, if you take some curves and you just kind of, you take some continuous curves and you kind of align them with the vector field, like continuous curves, we call these flow curves or streamlines. So what I did here is I took the original vector field and I just started at a point and I just drew a curve and kind of followed the direction in which the arrows are telling us to move. All right. So if you look down here, I'm kind of following the arrows. So this is what we'd call called the flow curves of the vector field, also called streamlines. Okay, it gives you a nice kind of visual of what's happening. Everything's kind of, you can see the arrows on the streamlines as well. It's indicating the direction of movement. Okay, so let's look at an example. 3 examples. We're going to sketch some representative vectors of these vector fields. These are all 2-dimensional vector fields. Let's start with the first one. We're also going to graph their flow curves. That part's easy. So let's start with the vector fields. So first thing you want to do is set up some field points. We're doing this one right here. Oh, here it is right there. And then we're going to graph vectors at each one of these field points. So for example, let's say we wanted to graph the vector right here at 1, 1. We would plug in an x value of 1 and a y value of 1 into the vector valued function. Now, an x value of 1, the y is actually not in there, so we don't need it. All we need is the x value. So we're going to get out the vector 0, 1, which you could represent with this vector right there. You'll notice that this is the vector 0, 1. It points upward, has no horizontal component, only a vertical component of 1. And then we could do this at another point too. We could do it at, let's say, this point right here at 2, 1. So you'd plug in 2, 1 into the vector field and you get out the vector 0, 2. And you could do this for, you know, any ordered pair of points. And if you were to do this at every ordered pair of points, and then you were to shrink them down proportionally, you'll get this vector field. So what you'll notice is the vectors get larger as we move away from the y-axis in both directions, although they do point downward as we move in the leftward direction. So this type of vector field is called a shear field. It's called shearing because you can see there's a shearing effect, an upward and downward vectors moving against each other, and the sharing is happening right down the y-axis. And by the way, these would be the flow curves. So on the right, the flow curves are all straight lines directed upward, and on the left, all the flow curves are straight lines directed downward. Okay, so that's the first one. Let's look at this next one. This is also a two-dimensional vector field. We are putting this restriction that the magnitude of y is between -1 and 1. So what this means is we're only looking at the vector field in this region. So we can ignore everything above 1 and below -1. So let's graph the vector field, and we're going to ignore everything up here above 1, and we'll ignore everything down here below -1. So the first thing we want to do is set up some field points, and then we're going to graph some vectors at each one of these field points. So for example, we could plug in 1 for x and 0.4 for y. And if we did that, 1 for x and 0.4 for y, the x isn't being used, but the 0.4 is. Let's see, 0.4 squared is 0.16, so 1 minus 0.16 is 0.86, so 0.86 or 0.84. So it's going to be the vector 0.840, which is a vector to the right of length 0.84. And we would do this at every single point, every single one of those field points. What you'll notice is as we move closer to y equals -1, the length of the vectors gets shorter. As we move towards the x-axis, they kind of max out in length. And then as we move up to positive y values, they shorten. So for negative y values, they shorten as we move closer to -1, and for larger y values, they shorten as we move closer to +1. You should notice that the x doesn't matter. If you move left and right, it's not changing the vector at all. Remember, you can pick up vectors, it doesn't change them. So that's the same vector as that one. These are all the same vector. And hopefully that makes sense, because the x value isn't even included in the vector field, so it shouldn't make a difference. So if we went ahead and plotted all of those vectors and shrunk them down accordingly so that they're proportional in size, we could get a general representative picture of what the vector field looks like so. So we call this a channel flow. This is kind of how maybe, let's say you had a stream or a river of water. This is how the water would flow through the stream, through a channel. The water moves fastest if you're in the middle. So if you're in a little raft and you're moving down this river, you'll move fastest down the middle. And as you get closer to the sides, the friction will kind of slow you down. Over here, you won't be moving as fast, and same thing down here. And by the way, these are the flow curves right there in blue. Okay, let's do one more. Let's do this one. This is a rotational vector field, but let's check it out. So same thing, we start with some field points, and then we would, pick a bunch of these field points and, calculate their vectors. So we could go to 1, 2, 1 for x, 2 for y, plug it in, then plot the resulting vector at that point. And we could do that for every single one of these points. And what you'll notice is as you get further away from the origin, the vectors get longer. As you get closer to the origin, the vectors get shorter. So if you were to plot them all and scale them down proportionately, your vector field would look like this, which looks kind of like a, I guess maybe looking down into a toilet, right? The circular flow or rotational flow of water in a toilet. And this is what the flow curves would look like. Just kind of go around in this counterclockwise direction, like so. Okay. One of the things to note is that it can be useful to take a vector field. Remember, the first component's always your f function, and the second's the g function. And let's say you wanted to know the slope of any one of these vectors in here. Remember, slope is just the change in y over change in x, and that's what a vector is. It's, you know, it's got a change in x and a change in y. So if we take the change in y over the change in x, essentially this will give us the slope of any vector in our vector field. So for example, all these guys in this first vector field, if you take the g over the f, that's x over 0, that's undefined. All of these vectors have slopes which are undefined. Whereas this guy, if we take g over f, that's 0 over 1 minus y squared, which is essentially 0, as long as we're within one of, as long as y is less than, absolute value of y is less than 1, what'll happen is all of these vectors will have slope 0. And then for this last guy, if we took the change in y over change in x here, let's see, that would be g over f. That's negative x over y. That would be the slope of these vectors. Every single one of those vectors, you could find the slope just by plugging in. Let's say you want to find the slope of that one right there. You just plug in 1, 1 into this formula, and that would give you the slope of that vector. So that turns out to be pretty handy. We'll talk about that a little later. All right, so that's two-dimensional vector fields. So what about three-dimensional vector fields? Well, the idea is the same. If you remember, mathematically speaking, a vector field is just a vector valued function on R2. So for R3, a vector field in R3 is simply a vector valued function on R3. So, you know, the definition would look something like this. A vector field on a region D of R3 is a vector valued function that looks like this. You'll notice it takes 3 inputs, x, y, and z. You plug them into each of the component. We'll call that first function f, that second function g, and the third function h. And we'll throw triangular braces around them, turning them into a vector. So the output is a vector, making this a vector valued function. Okay. So we can graph these kind of the same way. You're going to set up some field points and find the vectors at each one of those field points. So let's just look at a couple examples here. Hopefully, clearly you can see that that's a three-dimensional vector field, right? It's got 3 components. There's your f function, your g function, and your h function. And for this vector field, we're only gonna look at the vector field for z values greater than or equal to 0. So that would be the upper half of the of space, right? So that'd be above the z equals 0 plane. Well, including the z equals 0 plane, I guess. Okay, so let's look and see what this one look like. You know, because there's 3 dimensions to work with here, it's a little harder to try and think or visualize what these are. However, I have a little technique to kind of help you out here. So first of all, here's the field. Here's a representative sample of field points you might want to try. Something like this. All right, and we're going to compute the vectors at each one of these field points. Okay, so for example, like 1, 1, 2 it's kind of hard to see, but that would be this vector right there, or that field point right there. So we plug 1, 1, 2, x equals 1, y equals 1, and z equals 2 into the vector valued function. You got a vector, and we plot that vector at that point. So here's a way you can kind of attempt to visualize what these look like. Look, if I look at the first 2 components, x, y, that's a vector field. I didn't actually graph that one, but let's see if we can do it here. I'm going to graph that vector field. I'll use that as another example. For example, vector field. And then what I'll do, I'll change this to an x and that to a y. X, y. There we go. Now we can see what it looks like. All right, so that's this vector field here. This is it's called a radial vector field. We'll talk about that in just a minute, but you'll notice all the vectors point directly straight outward, and they get larger as we move away from the origin. So if we were to, where are we? If we were to try and visualize this vector field, you can see that the first two components are basically one of those radial vector fields if you kind of ignore the z-axis. Essentially what I mean is if you look at it from above, it should look like that radial vector field we were just looking at. So I'm kind of ignoring the z by looking at it from above, and you can see that the vectors point outward. I'll throw in a few more. Essentially, you have a radial vector field in the kind of x and y directions. So the only thing left really is to kind of determine what this what the third component of the vector is, the vector field is, e to the negative z. So I'm going to back these off a little bit. 3. So here's what I want you to notice. You know, above these vectors look like kind of an outward, these outward vectors pointing outward. But if you look at the vectors, let's look at the z direction here. You'll notice the vectors at the bottom are tilted up quite a bit. And then as we kind of move upward, they're not tilted up as much. So that's indicating that the z component is kind of decreasing as we increase in z values. So let's think about what this is. When z equals 0, that would be in the floor. If you were to plug in z equals 0 into that third component, you get e to the 0, which is 1. So the z component for each of the vectors in the floor should be 1. That's what's tilting these vectors in the upward direction quite a bit. Now let's say we move up 1 unit in the z in the positive z dimension. So let's say it's at 1. So now you have e to the negative 1. That's 1 over e. What is 1 divided by e? It's about 0.3678, which is significantly less than 1. So what's going to happen here is that the vectors will still point upward, but they're only going to point upward at a rate of 0.368, whatever I said. And as you increase z, you can see that what's happening here is your third component there, it's still positive, but it's getting smaller. So that's why these vectors are kind of angling down as we get higher and higher. Okay, so that's a way to kind of visually understand what this vector field looks like. Of course, if you wanted to actually calculate these and graph them, you should probably use some software like Math3D will do these, or the Mathematica program, which I've been showing you. All right, here's another one. This guy right here. You'll notice the f and the g components, the first and second components, are both 0. The only thing that's changing here is the h component, the third component. So this thing, if you think about what these vectors are, they all point either upward or downward, right? Now we're going to stay because there's no x and y components. So this is a very boring vector field because the first two components, there's nothing there. Also, we're going to be restricted. Let's say we only want to look within that's a cylinder in R3, so that would be this guy. So we're going to ignore everything outside of that cylinder. Now, if we, you set up your field points, we just look at the ones inside the cylinder, and then we could create vectors at each one of those field points, and there's your vector field right there. And if you wanted to plot more vectors, you could do that. It's up to you how many. You want to plot enough to where you can kind of see the general appearance of what's happening. So this is another example of channel flow, but this is a three-dimensional example. So let's say you have a tube. Let me back this up a little bit. Let's say you have a tube and you have water flowing through the tube. the water will flow the fastest in the middle of the tube, and it will slow down towards the edges. You can see that because the lengths of the vectors are getting shorter as we get closer to the edges. Okay, so I had a problem with the, what do you call those, with those little water pumps in my kitchen a couple of years ago. And I hooked up this tube. I was connecting it from some water from the faucet to my fridge, which was up over the ceiling, and it was kind of a long way. And I went out and I just bought a tube, and I didn't really think about the diameter of the tube. So I got a small one because I thought it would be easier to install. And I turned the thing on, hoping the water would pump over, but it didn't. The problem was that the diameter of the tube that I got was so small that not enough flow of water was getting through the center. There was too much friction along the edges. So with a larger diameter tube, you'll have to have a stronger pump, but you'll have less friction for water moving in the middle. Okay, so that is a three-dimensional version of channel flow. Now, I've already kind of mentioned the two-dimensional radial vector field, so probably should have done that earlier, but that's okay. Let me fix this. Close that up. Okay. But let's still talk about them. So radial vector field, these are these vector fields that, I mean, we saw one already where everything pointed outward, but a radial vector field is a little more general than that. What it is it's a vector field where all the vectors either point directly toward or away from the origin at all points, except for the origin. So mathematically speaking, a radial vector field looks like this, right? It's a vector valued function that's given by taking a scalar function, any scalar function you want, and scalar multiplying it times this specific vector. That vector xy, that's a vector that points away from the origin, directly away from the origin at all times, no matter where you are in the xy space. So if you relabel this particular vector r, you can write your radial vector fields this way. Essentially what it is, a radial vector field is a sorry, there's some noise downstairs. Is a scalar multiply of this a function that's a scalar is a scalar function times that radial vector r. Okay, what this does, remember when you scalar multiply a vector, all it does is it scales it. It could reverse the direction, but in general, you know, it can't really change the direction. It has to scale it. So here's some examples of here's an example of a two-dimensional radial vector field. So the function I'm using here is that guy. So I'll call this that's our function f in front, and there's that radial vector r. That's the specific vector xy. So I want you to notice that all of these vectors either point inward towards the origin or outward away from the origin. Every single one of them. This one points outward. This one points inward. That one points inward. That one points outward. All of them the same thing, and that's because we're taking scalar multiples of xy, and the scalar is a scalar function, right? It can change depending on what x value you plug in. All right, so that is a radial vector field on R2. Here's a radial vector field on R3. It's the same idea, only your radial vector that you're using is actually the xyz vector. That's the particular vector. This vector points directly outward from the origin. So we're basically going to take any scalar function and multiply it times that radial vector, which we can call r. So Same thing here. All of these vectors are either going to point directly toward the center or away toward the origin or away from the origin, except at the origin. Nothing happens there. It's just the zero vector. Okay, so same kind of idea, just in 3 dimensions now. So here's an example of a 3-dimensional radial vector field. So there's my radial vector xyz, but here's the scalar function. In this particular case, I'm choosing cosine x. So if I were to graph this, say using the Wolfram system or using that Math 3D, it's going to look something like this. So what I want you to notice is that every single one of these vectors either is pointing inward towards the origin or is pointing outward away from the origin. Okay. All right. Now, let's say that we have a vector field that happens to satisfy this form. So in other words, there's your radial vector xyz. And let's say that you take the magnitude of that xyz vector, raise it to the pth power, and you use that for the vector, for the scalar function sitting out front. These vector fields are of particular interest to us because they frequently occur in nature. You'll see them in your physics classes. For example, this vector field here, that one right there, it's got a negative in front, but essentially it's the same idea. You can see that I've got my radial vector, that's the xyz vector here. And then I've got the magnitude of the radial vector cube downstairs. So that would be this guy downstairs. That would be the magnitude of the radial vector, and that would be the magnitude cubed. Note that the magnitude of this thing is just 1 over the magnitude of r squared. That would be easy to find if you just took the magnitude of this guy, put absolute values around that, get rid of that negative, and you can see that you have the magnitude of every vector in that vector field is 1 over the magnitude of r squared. This actually agrees with Newton's inverse square law of gravitation. So in other words, we're talking about the gravitational forces between 2-point objects. For example, me and the Earth, right? So there's a force getting pulled down that's pulling me down towards the center of the Earth, and it's given the magnitude of that force is 1 over the magnitude of the radial vector squared. So it's this would be like that Earth one I showed you earlier. This is a gravitational vector field where you have the mass at the center. That would be the Earth, and you can see that the vectors get longer as we get closer to the center. All right, so normal and tangent vectors. What was I talking about here? Let's get rid of those guys. There we go. Okay. So let's say that we have a circle. Clearly that's a circle as long as, well, even if a wasn't greater than 0, but we'll assume a is greater than 0. That's a circle of radius a. So here's a circle of radius a down here. Let's get rid of that guy. Ignore the vectors for right now, but you can see you can make that. So here's a circle of radius 2. So here a would be 2. Here a would be 1. Let's stick it at 1. We're going to show that at each point on C, which is the circle, the radial vector field given by that guy, notice that's r over the magnitude of r, would be another way of writing it, right? So I guess I could write that absolute r, those bold. Oops, no. Another way of writing that. this is a radial vector field. So let's actually graph it. It looks like so. What you'll notice is that all of these vectors have the same length and they all point directly straight outward. And it's no surprise because if you remember what happens if you take a vector and you divide by its length, right? You'll normalize the vector so it has length 1. So this vector field, every vector at every point points straight outward with length 1, except for the origin, nothing happens there. Okay? So we're going to show that at each point on the circle, this radial vector field here is orthogonal to the curve C. So let's zoom in. Oops. I mean, hopefully you can see that from the graph. I mean, each one of those vectors as we walk along this thing are orthogonal or 90 degrees or perpendicular to the curve. So visually, this kind of makes sense, but we want to show this is true. So here's what we're going to do. We're going to do a little trick here. We're going to take our curve C, this guy right here, and we're going to basically create a function out of the left side, a surface. So I'm going to let G be x squared plus y squared. So now we've got this elliptic paraboloid that's cup-shaped up. It's got a vertex at the origin in 3 dimensions. And what you should notice is that this guy right here, this surface, if we set the surface equal to a squared, then that's a level curve of the surface. And that's precisely what this is. The curve C is a level curve of this elliptic paraboloid. So we're thinking of this curve in a funny way. We're thinking of it as the level curve of a 3-dimensional surface, which is strange, but it turns out to be helpful if you think of it like that. So what do we know about a function like this, right? Well, that's our paraboloid, elliptic paraboloid. We know that if we take the gradient of G, we know that the gradient of G has to be orthogonal to the level curves. That's something we learned in a previous section. Well, look at the gradient of G. We take this guy and find the gradient. It would be gx and gy. Well, that's the vector 2, the scalar multiple 2 times the vector xy, or the radial vector. Okay, well, look, your vector field, the one that was given, this is what it was given as. We could rewrite it like this. We could pull, that's just a scalar downstairs, so we could pull it out front. So look, I've got the gradient of G is this guy, and I've got the vector field F is this guy. Notice these vectors are parallel. These are just scalars in front. The only difference between these vectors is the scalars, is how long they are, essentially. So that means that that these two vectors must be parallel to each other. So the gradient of G and F must be parallel. So what does that mean? That means F is orthogonal to the line tangent to C. Okay, you might want to read through that argument a couple times, but that's the idea. For the next one, now we've got a rotational vector field. So in this vector field, there's your rotational vector field we discussed earlier. And then we divide by its length, essentially that makes all the vectors have length 1. So this is what the vector field looks like. And we're going to show that each point of the same curve C is parallel to the, let's see, show that each point C, okay, the vector field is parallel to the line tangent to C. So yeah, if we look at a line tangent to C, the vector field seems to always be parallel to the tangent lines. So to prove something like this, what we could do is just take the gradient of G, what we found in the first part up here, and dot it with the vector field G. And that if we dot those together, that'll prove that the gradient of G and G is orthogonal, which means G is parallel to the line tangent to C. So if we take the gradient and G and we dot them together, you could pull out the scalars, pull them out in front, and then dot the two vectors. And when you dot the two vectors, you end up getting 0 there. So it kills everything. So yeah, that does it. That proves that the gradient of G and the vector field are orthogonal to each other. So that means G is parallel to the line tangent to C. Okay. All right. You might want to read through and think through that process there. It's a little hard to think through all at once, but if you read through it, hopefully that makes sense. And gradient fields and potential functions. So what you have probably noticed by now throughout Calculus 3 is we keep taking ideas from Calc 1 and Calc 2 and we keep just extending them up to 2 and 3 dimensions. So there's no difference here. Essentially, what we're going to do is we're going to take the idea of derivatives and antiderivatives from Calc 1 and extend them up to higher dimensions. And it has something to do with gradient fields, with fields, I should say. We haven't talked about gradient fields yet. So what is a gradient field? Well, let's say that you start with a scalar function phi. Let's say it's an R2. That would be a surface, right? Phi of x and y. Or you could do R3, but let's think about R2. You can create a vector field out of that scalar function. All you have to do is take the gradient operator of phi. And if you think about what that is, let's see, it was Nabla. For 2 dimensions, it would be that one. And for, 3 dimensions, it would be that one. But you'll notice what you get a vector out, and that's a vector valued function. That's what this ends up being. So what's interesting here is we start with a scalar valued function, which is like a surface or a hypersurface in R3 or in R4. And you can take the gradient vector of it, gradient operator, and it turns it into a gradient field or a field, and we call that field the gradient field of phi. So it's kind of like taking the derivative, only it's a little different, because in Calc 1, I'd give you a function, and I'd ask you to differentiate it, and you just differentiate the function, you get another function, another real valued function. But here it's a little strange because we're starting with a scalar valued function, which is a function of, let's say, 2 or 3 variables. And when we differentiate it, but we're not really differentiating, we're taking the gradient. You end up getting a vector field, either in R2 or R3. So for example, here's a scalar valued function, that's a surface in R3. When we take the gradient of it, we end up getting a 2-dimensional vector field. So these are different objects, right? We're starting with a surface, and then we're taking the gradient and we're getting a vector field out of it, but it's synonymous or analogous in the fact that it's kind of like differentiation. By the way, it works in reverse too. If I started with a vector field, maybe there'd be a way to come up with the kind of anti gradient field, or the reverse direction, to find the potential function, or I'm sorry, the function that would that when we take the gradient of it, we got f, we got big F. We call this the potential function. So this is kind of like the antiderivative, and this is kind of like the derivative. So let's go back to Calc 1 just to solidify this a little bit. In Calculus 1, if I gave you a function like that, we'll call it capital F. It has nothing to do with that F, but we'll just call it capital F. If you differentiate it, the derivative of this guy would be 2x. It's also a function. Both of these are real valued function. The antiderivative of little f would be big F, right? These are both functions of one real valued functions of one variable. So essentially, here we're kind of taking the same idea, but kind of including an extra variable. So instead of having a function of one variable, now we have a function of two variables. And instead of differentiating to get this, we're going to take the gradient operator, which is a kind of a way of differentiating, right? They're partials. That's the partials are derivatives. So partial there, partial there. And this would be like our derivative, but we call it the gradient field because it is a field. And then in the opposite direction, if you start with this guy and you wanted to work up, we'd call that the antiderivative. But for us, if you start with the gradient field and you wanted to work your way back, we'd call that the potential function. Okay, or the potential. So essentially this gradient operator, which by the way, it's called nabla, it's playing the role of the derivative from calculus 1. And everything's kind of synonymous, including the fact that if you were to find all antiderivatives of a function like this, you actually get capital F of x equals x squared plus c. So the extra constants don't make a difference. The same is true when we're finding potential functions for a vector field. When you add the c, it doesn't make any difference because when you do take the partial derivatives, the c disappears anyway. Okay, so I hope you can see that gradient fields of potential functions are kind of taking the place of derivatives and antiderivatives. And essentially this is taking the place of the old differential operator. Okay, so let's compute some gradient fields in R2. So let's say we start, here's a scalar valued function, right? It's a surface. It's let's see, what would this look like? It'd be an upside down elliptic paraboloid shifted up 200 units. Its vertex is on the z-axis. Okay, so this is a temperature function. We're defining on a circular disk of radius 5. So, you could probably try and visualize this thing over this disk of radius 5. The temperature is going to be greatest at the origin of the disk when x and y are both 0. It'll be 200. And as we move away from the origin to the edge of the disk with radius 5, it looks like the temperature is going to drop to 175 degrees once we hit the edge of the disk in any direction. But let's find the gradient field of this scalar valued function, and we'll interpret it. So the gradient field's easy. All you got to do is take the gradient or nabla of t. All right, well, that's just the partial of the first component with respect to t, respect to x, partial of second component with respect to y. So that's the vector field that we get out. So this scalar function, once we take the gradient of it gives us a different object. It gives us a vector field. By the way, this is a radial vector field in R2 pointing inward towards the origin. You could find the magnitude of the field if you wanted. This would be the magnitude of each one of the vectors inside that vector field. And we could do the same. So there's your gradient field we were after right there. What else? Same thing here. If you start with, this is a scalar valued function, so this is a surface. You could take the gradient of phi. I'm not sure if you remember this, but the derivative of tan inverse of u is 1 over 1 plus u squared times, du. So there's your derivatives. Don't forget the chain rule right there. You could simplify it. So there's the gradient field that's created out of this potential function. Yeah, okay. All right. So finally, we've talked about these gradient fields and their potential functions. It turns out that there's these nice visuals that show up a lot in physics. And the visuals that you see will show, oftentimes they'll show flow curves of vector fields, and they'll show the level curves of the potential function associated with that vector field. Those level curves, we actually give a name. They're called equipotential curves. They're really just level curves of the potential function phi. But basically the level curves of whatever that surface is. And we call them potential curves because these are the curves for which the potential function is constant. That's the potential function. So let's say, so the figure below displays some level curves or potential functions for some scalar function phi. Here's the level curve. So you got to imagine there's a surface associated with this, right? And then if you were to graph the associated gradient field for this guy, that's what it would look like. But the most important thing I want you to pay attention to here is look how the gradient field, all of the vectors in the gradient field are related to the equipotential curves, the level curves. They're always at 90 degrees, right? And of course, we know that this is because the gradient field consists of the gradient vectors, which always point in the direction of steepest descent. So this makes sense. Okay. All right. So it turns out that, the physical meaning of these gradient fields is pretty useful because essentially what it means is it tells us the direction of steepest descent. So if phi, let's say, represents temperature in a conducting material, then the vector field associated with it just tells us the direction in which the temperature increases most rapidly. Or if phi represents the elevation of a wavy surface, right, then its gradient field points in the direction steepest ascent, so water flows down, so it'd be the direction opposite water flow. Okay. Sometimes it's nicer to plot these things with flow curves. So instead of vectors, we'll just draw some straight lines. I didn't include that picture here, but you can kind of get the idea. All right, so let's see. Let's graph some equipotential curves in R2. So what we're going to do? No, we're going to find them. All right, so let's say that we have a function there, and it's an equipotential. I'm sorry, it's a potential function, so it has a gradient field. Let's go ahead and find the equipotential curves. Oh, I was supposed to show them. Okay, unfortunately, I don't have a graph. That's okay. Let's go ahead and just find the gradient field associated with phi. So to get the gradient field, of course, you're just going to take the gradient of phi. So there's your gradient field. That's a rotational vector field. The equipotential curves of this thing are just the level curves of it. So we could set this guy equal to c. And where c is some constant. And let's see, the slope of any point on the level curve. Oh, okay. So let's say we wanted to find the slope at any point on this level curve. We could just use that rule for finding slopes that we learned in chapter 15, I believe, where it's negative phi x over phi y. We could find phi x and phi y and plug those in, and this would be the slope at any point on the level curve, C. Now, we're asked to find the gradient field associated with phi, which we did, and verify that the gradient field is orthogonal to the equipotential curve at 2, 1. So we've got the slope everywhere. So if we plug in 2, 1, we'll find the slope at that point, 2, 1, the slope of the equipotential curve. Okay, so basically the tangent vector to the point in that direction, if you think about what that means, 2, slope of 2 means you're going to go, let's see, up 2 to the right 1. So the vector associated with that up 2 to the right 1 would be that vector there. So, and then we know the gradient field at the point 2, 1 yields this vector. And now if we dot this vector and this vector together, we get 0, which indicates that the gradient field is orthogonal to the equipotential curve. Okay, so and we'll skip that one. You guys can read through that on your own. All right, so that's for 2 dimensions. So the level curves of potential function phi of f in R2 are called equipotential curves. If you can imagine, we could take the same idea and extend it up to 3 dimensions. Only instead of curves, we have surfaces. So the level surfaces of a potential function phi of f in R3, we call these equipotential surfaces. So for example, let's say we had this hypersurface, right? We could find its gradient field just by finding the partials with respect to x, y, and z, factoring out the 2. So there's the associated gradient field. So that's the potential function, that's the gradient field. And that's a radial vector field. Now, if we were to graph all the level surfaces of these guys, they would be spheres. And we were to graph all the vector, this vector field, that'd be a radial vector field. So here they are. So I plotted them both in the same plot. And what you'll notice is that the level surfaces, which are the spheres there, are all perfectly orthogonal to the vector field. So it's the same case in R2. It's the same case in R3. Okay, and remember, those blue vectors, they always point in the direction of steepest ascent of the hypersurface. So even though we can't see what direction that is, as far as the 4 dimensions needed to graph this, we do know that if we move in this direction, outward away from the origin in the XYZ direction, our hypersurface will increase in hyperheight the fastest. Okay. All right. I know that's a lot, but hopefully that helps you digest some of it. All right. Good luck.